Hello, everybody. Sorry, I'm a little bit late. Oh, I guess I'm still early for the 9 o'clock, but yeah, we had a little bit of issues getting started today, but we're here. Does everybody want to say hello, or who's in the chat today? And then we could get started with class. Miriam, Liza, Emma, good morning to you all. Thanks for showing up. Maddie, good morning. Okay. Well, yeah, so we left off in the middle of an example on Friday, I guess. And if you tried out the example, that's great. I realized that I may have had a typo. So you'll have another example that looks very similar to the previous example. The process is the same. The numbers will just be a little bit cleaner in my example than they were in the one that we wrote out on Friday. So we'll let Noah Shutong, good morning. So we'll let A be the matrix 7, -4, 2, 1, and find a formula for A to the K. So we raise, Emma, excellent observation. What a disaster this could have been. Okay, let's do the simultaneous sip. I have literally not spoken since our last or since my calc class. So I'm a little off right now because, this whole, being locked in place thing is driving me a little bit nuts, but we're doing good. We're doing good. So Taylor and Emma, good job. You're paying attention. Yeah. Okay, so we have this matrix. We want to find a formula for A to the K. William, good morning. And what we could do is just multiply it a bunch of times and see if we have a pattern, but we're also given that A equals P D P inverse, where P is the matrix, and this is where my typo was, 1, 1, -1, -2, and D 5, 0, 0, 3. So we want to find a formula for A to the K. So let's find A squared, then let's find A to the third and see if we can figure out a pattern. I guess first what we should do is find P inverse, right? Because that's going to be part of A. A is P, D, P inverse. And this was given to us. You could imagine that by the end of today's class, we'll have a way of figuring out what P and D would be without having it handed to us. But for now, we don't know those methods. Okay, so how do we find the inverse of a 2x2 matrix? Right, it's 1 over the determinant of P times the matrix where you switch the entries in the main diagonal and you turn the entries in the other diagonal negative. And the determinant of P is you multiply down the main diagonal and subtract off when you go to the other diagonal. right? -2 plus 1 is -1. And so P inverse is 1 over -1 times this matrix. So it's 2, 1, minus 1, minus 1. Okay, so you could check just by computation that A is equal to 1, 1, minus 1, minus 2 times the matrix 5, 0, 0, 3 times the matrix 2, minus 1, 1, minus 1. You could go through and check this if you'd like. We're not going to. But we want to find a formula for a to the k, so let's find a squared. So that's P d P inverse times P d P inverse. P inverse times P is the identity matrix. So we don't have to include this. This is the same thing as P d squared P inverse. So far, so good. If you could give some sort of feedback to me in the comments, that would be great. We could continue finding a to the third. Well, that's just a squared times a. Which is P d squared P inverse times P d P inverse. And again, look, the P inverse and the P cancel out. And we're left with P d to the third P inverse. Okay, and we're not going to go through and prove this, but you could use some sort of inductive proof to show that a to the k is equal to P d to the k P inverse. And we know what d to the k is because we did this computation as our previous example. Okay, and so we have all we need. A to the k is equal to, so a raised to any number is equal to p, which is 1, 1, -1, 1, -2, times d to the k times P inverse. 2, -1, 1, -1. Okay, I'll pause for a second to answer some questions. How do you get P d to the third P inverse? Here. So to get a to the third, that's the same thing as taking a squared times a. We saw that a squared is the matrix P d squared P inverse. So P d squared P inverse times A, which is P d P inverse. P inverse times P is the identity matrix. So that we don't have to include this anymore. So it's really P times d squared times d times P inverse. D squared times d is d to the third. Okay, and if we were to do this multiplication out, we're going to get 2 times 5 to the k minus 3 to the k as our first entry, 5 to the k minus 3 to the k as our next entry, 2 times 3 to the k minus 2 times 5 to the k as our bottom left entry. And 2 times 3 to the k minus 5 to the k times our third entry. Why would the first p and last p inverse not cancel out as well? Well, remember that multiplication by matrices doesn't commute. So we're not allowed to switch the order here. So since they're separated by this d to the third, they have to be right next to each other in order to cancel out. We're not allowed to switch the order to cancel them out like you would with normal numbers. Since we don't have multiplication doesn't commute, with matrix multiplication isn't commutative, so we're not allowed to kind of switch this order and then cancel them out. So if they're separated by a matrix in between, they don't cancel out. Okay, and so if we want to find a to the k, let's say we wanted to find a to the 100, like that one homework question that I gave you that one time about determinants, you just plug in k equals 100 and equal to into here and simplify. So this is how a computer would do. This is how a computer raises a matrix to a power. Is they first diagonalize the matrix, which we're going to define in a second, and then do it like this. Okay, so I'm going to start writing out another definition. But if you have any questions about this example, I'll get to them when it gets to me. So a square matrix A is diagonalizable if there exists an invertible matrix P and a diagonal matrix D such that A equals P, D, P inverse. Okay, so we say a matrix is diagonalizable if we could express A as P times D, where D is diagonal, times P inverse. And now you may ask, when is it the case that we have a diagonal matrix, a diagonalizable matrix? You saw here that our matrix 7, -4, 2, 1 was diagonalizable. But you could imagine there's some matrices that this doesn't work. So we're gonna write a theorem that tells us when we could diagonalize our matrix, and the theorem will tell us how to find P and D. Okay, so this theorem that we're about to state will be useful when we want to diagonalize a matrix. It will tell us how to get this matrix P and the matrix D. So this is the diagonalization theorem. And it says an n by n matrix A is diagonalizable If and only if A has n linearly independent eigenvectors. Okay, so our test to check if A is diagonalizable is we have to find all of its eigenvectors and check if there's n linearly independent ones. Okay? And so if it's true that it is diagonalizable, then the eigenvectors form the columns of P. So in this case, the columns of P are the eigenvectors of A, and the diagonal entries of D, which is our matrix, our diagonal matrix, are the eigenvalues. Okay, so in order to diagonalize a matrix, what we have to do is find the eigenvalues and find the eigenvectors, and then we'll put them together into matrix form. Okay, are there any questions? I would say if you have a question, ask the question. If you don't have a question, maybe post a smiley face or a thumbs up or something in the chat, just so I can get a little bit of feedback. Okay, so let's do an example to see how we can apply this theorem. We got a smiley face, we have a heart. Okay, good. You guys love the diagonalization theorem. Well, it's good because it's useful. Patrick with a smiley face. Okay, so let A be the matrix 1, -3, 3, 3, -5, 3, and 3, -3, 1. So one can check that the characteristic polynomial is negative lambda minus 1, lambda plus 2 squared. So I'm giving you the characteristic polynomial. And so the question is, diagonalize A if possible. Okay, so while I'm writing this down, does somebody want to put in the chat how they plan to diagonalize A, or how they're going to check if it even is possible? And while you either are typing your answer in the chat, I'll give you a few minutes to try to work this out. but we're going to use this theorem. Right, so we want to, basically what we want to do is find the eigenvectors, which we could find using our characteristic polynomial, and then find a basis for each of the corresponding eigenspaces. And then we're going to count the number of basis elements in each of the eigenspaces. And if we have 3, then we're diagonalizable. Okay, so I'll give you, let's say, like 3 minutes to get started on this. During that time, I'll answer any questions that people have in the chat. Or I'll just stand near my laptop awkwardly in silence. And if you're not sure how to do this problem, tell us in the chat what you did over the weekend to stay busy during the stay-at-home time. Watch movies, read a book, do math, do homework. What did you do? I'm interested because I did nothing. Miriam ran a lot. I actually went for a few runs this weekend also. Yeah, you gotta just stay busy. Emma hung out with her sister. That's nice. It's nice if you have family around. Give someone to hang out with. Taylor cleaned the house. You know, believe it or not, my apartment is a total mess, and I decided to not clean this weekend. Maybe that will be this week's job. Okay, enough of that. Unless people want to share still. All right, so we'll kind of go through one step at a time of how we're going to do this. Just because this is kind of an important topic. So our first step, find the eigenvalues. Okay, hold on. Before we get to this, Taylor asked a question. Also, do we have to use a minus lambda I to find the bases? Yes, yes. So that's how we would find the bases for these eigenspaces. But the question is, well, step 1, find the eigenvalues. And so I'll get to your, you'll see that we work out your question, Taylor. But my question is, what are the eigenvalues of our matrix? So to get the eigenvalues, you set our characteristic polynomial equal to 0. And you get, right, 1 and -2. Okay, step 2. find bases for each of the corresponding eigenspaces. Okay, so we'll start with 1. So we'll look at the matrix A minus 1 times I. Which is the matrix 0, minus 3, 3, 3, minus 6, 3, 3, minus 3, 0. Okay, and we want to find the null space of this matrix, right? That's the same thing as finding the eigenspace corresponding to lambda equals 1. And so we can row reduce this. So notice if you add the third and the first rows to row 2, it goes to 0. So this row reduces to 1, 1, 0, 0, 1, 1, 0, 0, 0, which row reduces to 1, 0, 0, 0, 1, 0, minus 1, 1, 0. And so we have the equations x1 minus x3 equals 0, x2 plus x3 equals 0. Which we could work out to be x3 times the vector 1 minus 1, 1. I skipped a few steps, but we've done this type of example a bunch that you could verify this on your own. So that's one eigenvector. Now we're going to repeat with the eigenvalue lambda equals -2, and we should hope to get 2 eigenvectors. If we don't get 2 eigenvectors, then we won't have. We need n. We need 3. We need 3 eigenvectors total. We have 1 so far, so we need 2 more. If we don't get all 3, then we're not going to be able to diagonalize this. Okay, so let's look at the matrix A plus 2i. That's 3, 3, 3. Minus 3, minus 3, minus 3, 3, 3, 3. This row reduces to 1, 1, 1, 0, 0, 0. And so we get, right, we have 2 free variables here. How do we know how many eigenvectors we need? It's from here. We need n. N is the number of rows and columns of our matrix. So in this case, we have a 3 by 3 matrix. So we're going to need 3. So this is x1 is equal to negative x2 minus x3. And so we have 2 more eigenvectors. So we have 1, 2, 3 eigenvectors. We're good to go. And so That's step 2, which is the hard part of the question. Step 3 is construct P. Okay, and the way we get P is we just write down the eigenvectors. These are the columns, right? The columns of P are the eigenvectors of A. Okay, and then our last step is construct D. Okay, and I erased part of it, but luckily we saved the part about D. The entries of D are the corresponding eigenvalues. So D is a diagonal matrix, so all the non-diagonal entries are 0. But the eigenvalue corresponding to this eigenvector was lambda equals 1. And the eigenvalues corresponding to the other 2 eigenvectors were negative 2. Okay, and so you could check that A equals 1 minus 1, 1, minus 1, 1, 0, minus 1, 0, 1, times 1, 0, 0, 0 minus 2, 0, 0, 0 minus 2. So you could check that A is equal to P, D, P inverse. We didn't find P inverse, but the way you'd find it, remember, you'd take P and write it next to the identity matrix, row reduce P until you get the identity matrix, and what's left over is P inverse. Okay, so ask any questions you have in the chat. I'll write out the next example. The next example is we'll do the same problem except with a different matrix. So the example is repeat. Repeat the previous example with A equals 2, negative 4, 3, 4, negative 6, 3, 3, negative 3, 1. And the characteristic polynomial is negative lambda minus 1, lambda plus 2 squared. So this matrix has an identical characteristic polynomial. Emma asks, does it matter the order of the columns that make up P? Yes and no. We just have to make sure that if you put the eigenvector corresponding to 1 in the first column, then the first entry of D has to be the 1. The order of the eigenvectors corresponding to negative 2 don't matter. We just have to make sure that the corresponding entries in D are the correct eigenvalues. Can you remind me how to construct D? Yeah, you just read off. It's going to be a diagonal matrix, so the entries are only along the diagonal, and they're just the eigenvalues. So what was the eigenvalue corresponding to this matrix? That was lambda equals 1. So we put a 1 here. What was the eigenvalue corresponding to the other two vectors? It was -2. So we put -2s along the diagonal. Okay, so the eigenvalues for A are 1 and -2 again. And so again, we're going to just find bases for the eigenspace corresponding to A. I mean, corresponding to each of these lambda values. So I'm not going to go through all the steps like we did last time, but you could check, and I would recommend doing this out after class as practice. So basis for lambda equals 1 is the vector 1 minus 1, 1. So you just go through the same steps, look at A minus 1i, and find the null space for that. And a basis for the eigenspace when lambda equals -2 is the vector -1, 1, 0. So what can we conclude? Well, we count the number of vectors. We need to have at least 3, or we need to have exactly 3, and there's only 2. So you're right, Taylor. It is not diagonalizable. So I know I didn't actually go through the steps here, but you should check on your own that these are bases for the eigenspaces. Yeah, Cal, exactly. Since there are not 3 eigenvectors, it is not diagonalizable. So okay, so here's an example of a matrix with a couple of eigenvalues, but it's not diagonalizable. So there are non-diagonalizable matrices. Okay, so now let's state another theorem that will give us another way to check if a matrix is diagonalizable. So an n by n matrix with n distinct eigenvalues is diagonalizable. Okay, so if we had 3 eigenvalues, we would automatically know that it's diagonalizable here. We wouldn't have to go through and find the eigenvectors. But if we wanted to diagonalize it, then we would need to find the eigenvectors. But if we're just testing if it is diagonalizable, we just can count eigenvalues in some cases. Okay, here's a quick example. Determine if A is diagonalizable, and then just maybe, a sentence Y. A is the matrix 5, 0, 0, negative 8, 0, 0, 1, 7, negative 2. So I'll give you, just a minute here. Is A diagonalizable? So in the chat, yes or no, is it diagonalizable and why? And it's fine to just put question marks or write out I don't know or a frown face or something if you're not quite sure. The eigenvalues are 5, 0, negative 2. So it is diagonalizable. That is exactly right. Yeah, so we have a triangular matrix, right? Everything below the main diagonal is 0. And so we had a theorem that told us how to find the eigenvalues of triangular matrix. They're just the entries. So we have 3 distinct eigenvalues, and so we could use this theorem. A 3 by 3 matrix with 3 distinct eigenvalues is diagonalizable. Right, so the eigenvalues of A are 5, 0, negative 2. By the previous theorem, A is diagonalizable. Okay, so let's state one more theorem and then look at one last example. Okay, so A is the n by n matrix. The theorem says all right, we do not have enough space for that word. Diagonalizable. So then A is diagonalizable if and only if the sum of the dimensions of its eigenspaces is equal to n. Okay, so this is basically what we saw from the example previously. We needed 3 eigenvectors here. We only had 2. If we added up the dimensions here, the dimension of this eigenspace was 1. The dimension of this eigenspace is also 1. 1 plus 1 is not equal to 3. So this theorem tells us is another way to check that example, this matrix was not diagonalizable. Okay, so let's write out an example and we'll start class with this tomorrow. So just the example is diagonalize A if possible. Okay, so we obviously don't have time to work this out, but we'll start class with this tomorrow. I'll tell you what the answer is if you want to check, or what the answer is. Yes, it is possible. So try to diagonalize this tonight, and then tomorrow we'll start class with that. Yeah, but other than that, I think that's all I have for today. There's no homework this week because we have the take-home test on starting on Friday. Just make sure you hit the like button before you leave. Really helps out the channel. We're on that quest to 1,000 subscribers. Already almost over halfway there. But yeah, I'll hang around for a few minutes to answer questions. Yes, we will have class on Friday. Yeah, so the test will start at 9:50 on Friday, and then it will go until Monday morning. So you'll have Friday, Saturday, and Sunday to work on the take-home test. Correct, Emma. No quiz. Just the take-home. Thank you all for coming. Feel free to stay for calculus if you'd like. That starts in 13 minutes. Obviously, I don't expect you to do that. All right. You're welcome, everybody. Not that I really did anything. I'll see you all tomorrow. Maddie, will you post an answer to the study guide? Yeah, that's my goal for today, is to just crank out as many answers as possible. So hopefully I should be able to post a partial solution today. I'm going to just keep working on it a little bit at a time. All right. Well, if there's no more questions, I'm going to end the stream. So bye-bye, everybody.